Okay, I think I'll get started. It's kind of gone 10 to. Yeah, it's my first time at GOTO, first time in Denmark. It's lovely to be here. The sun is shining. Anyway, I work for Google. I'm a developer advocate. My name is Sam Dutton. On Twitter, I'm actually SW12. Sam Dutton on Twitter is someone completely different. Some guy in Arizona, I believe. Apparently, he just got bitten by a wasp. Anyway, seriously, if you want to follow along with these slides, they're at go.webrtc.appspot.com. If you're really obsessed, there's a GitHub repo, patches and issues, all that, really welcome. I'm, of course, going to talk about WebRTC. I'm going to talk about how you can build a WebRTC app, but I'd like to begin by kind of giving a bit of context to the project. So, WebRTC is a collaboration, as Robert said, to bring real-time communication to the browser. As a colleague of mine, Serge Lachapelle, said, human communication should be as natural in a web app as entering text in a text box. It's kind of, one of the last, maybe one of the last missing pieces in the browser. So the core values of the project have been that it must be, all the components must be open source, and that it must be free for developers to implement WebRTC apps and free for users. And of course, at the heart of this is video and audio communication, but also the ability to communicate arbitrary data between end users of WebRTC apps. And that this must be able to access the highest quality audio video streaming, but to do this in a way that was low cost for people to implement these apps. And as it turned out, the kind of core of this has been that WebRTC would work peer-to-peer. Traditional real-time communications apps, in this very, very oversimplified diagram, kind of corporate, difficult to implement, but also, going via kind of secondary systems. The kind of vision of WebRTC is this diagram with a white fluffy cloud in the middle. But, the point here is to enable peer-to-peer communication. As we'll see, things are never that simple. But that's the core of this, to enable, data and audio and video streaming between peers directly. So, to accomplish this, the WebRTC project had to do a number of things. They had to kind of define protocols and define the protocols that would be used by the project, the IETF, and then to build specs, standards with the W3C, so we have the WebRTC draft and media capture and streams and so on. And then to do this stuff, kind of the really difficult bit is to build these things into the browser. So we needed really good media and communication stack. Just a word about Jingle, because this is kind of at the core of a lot of the WebRTC work. Jingle is an extension to XMPP to enable audio, like voice and video, with chat. And libjingle is a C++ library developed by Google to implement that. And kind of network transport parts of that are at the core of WebRTC. And you'll hear a lot of stuff about libjingle if you kind of delve a bit into WebRTC. We've seen in parallel the development of high quality open source codecs, VP8 and Opus and so on. And the aim, of course, is for this to be building a new kind of communications ecosystem, a new way of communicating. So where are we now? We have WebRTC APIs implemented on Chrome and Chrome for Android, Firefox, and now Firefox for Android, which is great. Opera have said that they will be implementing on desktop and for mobile. Opera, of course, has moved to Blink, and we've now got native bindings for WebRTC in Java and most recently for iOS in Objective-C. One thing, by the way, that just appealed to me as a one-time Qt developer, Qt, the project, has just announced that they will be using Chromium, and what this means is that apps built with the Qt framework, embedded devices, lots of cross-platform potential. We'll have all this stuff, as they said, working out of the box. To me, that's really exciting. So we have, at the moment, something like, well, over 1 billion WebRTC endpoints, a lot more predicted for the near future over the next couple of years. So, you know, will this be the end of telephony as we know it? Time will tell, but I think that, you know, just looking at the kind of applications we've seen recently, there's some really interesting stuff already coming through. We just had the first TV interview done via WebRTC. This was in London a few weeks ago, done by Sky. In the old days, to do that, you know, you needed all this kit, all these people. You needed like these OB trucks and the staff to go with them. And they did this with a camera exactly like the one I've got here, and one of these Yeti mics, which is, I don't know, 100 euros. So that's, to me, is a, you know, fantastic potential there. So that's a little bit about the, I don't know, the vision of WebRTC. But just, you know, thinking about what we need to build real-time communication. So at the core, I guess, of real-time communication is the ability to access voice and video and to communicate that, you know, thinking about telephony and video chat and so on. And this is the kind of core use case for WebRTC. And for this, we need to accomplish 3 kinds of things. Firstly, we need to be able to get the audio and video. We need a way to get, you know, stuff from your mic and your camera. And secondly, we need to be able to communicate that data. And that turns out to be, of course, you know, very complex. And the third part is this ability to communicate arbitrary data, other types of data, as well as audio and video. So for this, we have 3 main JavaScript APIs. We have MediaStream, better known, I think, to most people from getUserMedia, a way of getting access to local audio and video from your mic and camera. And we have RTCPeerConnection, which is the API for establishing connections and communicating between peers. RTCDataChannel is kind of part of that, but this is the API for communicating arbitrary data. And I'll talk about this stuff later. So, MediaStream is this kind of, what's the word, abstraction of streaming media. We can get a media stream using the navigator getUserMedia method. A media stream represents like a single synchronized source of streaming data. And each media stream can have multiple media stream tracks, each of those representing audio or video. And we get one, like I say, using getUserMedia. And you can see in the example here in the diagram, we've actually got that broken down one step further, where an audio media stream track has a left channel and a right channel. And you can imagine variants on that theme. Navigator getUserMedia takes 3 arguments. The first of these is kind of interesting, but in this example, it's very simple. You can see the constraints object at the top there. All I'm saying here is, get me video. I don't care where it comes from, just the default device. That's all I want is video, no audio, nothing else. And then you can see in the success callback that that's passed a stream, a media stream, and then in this example, the simple example, we're setting that as the source of a video element. Let's see that in action now. So you notice when I've opened this page that's running getUserMedia, if you haven't seen this before, I'm allowing access to my camera and hopefully getting some, there we go, some video coming through there. If we just look at the code, let me bump that up a bit so you can see it. If we look at the stream object here, you can see I've got various properties there, and we could do things like stop the stream, which should freeze the getting of the video. If we delve into the stream a bit, if we get video tracks, whoops, you'll see that we can see one for each of the sources, which in this case is just the built-in camera, which has an ID and a kind and a label and so Just a word about permissions. If you run a WebRTC app, like using getUserMedia from HTTPS, you will only be asked the first time for access to the camera, microphone, and so on. This is really handy, you know, so people don't get repeatedly every time they use your app asked again and again and again. You can also do this in Chrome apps with the audio capture, video capture permissions. Something that is potentially really useful for testing is that you can run Chrome with a flag so that no permission is ever asked. Obviously, this is useful for, I don't know, unit testing situations where it's going to be difficult to try and have permission accepted. So it still enables you to run getUserMedia without having to OK that each time. And the UI gives the ability to change settings afterwards. A word of warning, I keep doing this. You can't run getUserMedia from your local file system. This comes back to bite me all the time. At the moment, you get this really baffling little permission denied message if you run getUserMedia locally. There are plans to give much better warning messages, but just a warning about those warnings, because it's... What's that? That's a good question. You know, a lot of APIs need to be run from a server, not run from the local file system. I don't really see the benefits for that, but I mean, Mike, you might have more. Yeah, well, Mike will talk to you afterwards. But yeah, it's a good question. I think, you know, the great thing working with WebRTC, that it's not a plugin, is that we have access to all these, you know, the kind of wealth of HTML and CSS and JavaScript. In this example, we've got getUserMedia getting video, and then the images from that are being plumbed into a canvas element. Then each pixel of that is being analyzed, and from that we're getting ASCII art, like as in real text, which is kind of nice. FaceCat, I know people may have, sorry if you may have seen all these, but I still love them. This uses the head tracker face tracking JavaScript library. Will it work? Oh yeah, there we go. With getUserMedia. So if I move around, I'm controlling the game with the position of my head, sort of. Anyway, you get the general idea. Eric Beitelman's lovely old CSS filters photo booth. Really simple here. You're getting images coming through from getUserMedia, and then you can just add CSS filters. Really straightforward to do some kind of crazy things. And then you can, I don't know why they're broken here, but you can then get those images and save them. Just simple stuff with CSS filters. Webcam Toy does kind of the same thing, but with WebGL. And if we have a look at that now, you'll see what I mean, that it's kind of the same process, and yeah, it's kind of weird sort of psychedelic. Okay, that'll do. Oh my God, that's just hideous. Anyway, if I was really nuts, I could share that with my friends. Just a word about constraints again. If you remember the simple example I gave, just said, give me video, default video, whatever, that's it. I didn't want audio because it would feed back, you know. Now, you can do some more interesting things with constraints. In particular, you can specify them to be mandatory for getUserMedia. If they're mandatory, then getUserMedia will have a tantrum if that constraint isn't met and will refuse to cooperate, and you won't get anywhere. If they're optional, then getUserMedia will try to fulfill that constraint, but will fall back to acting as if you'd never asked for that in the first place, if that's not possible. So for this, we've got things like resolution, facing mode, you know, choice of cameras, and so on. Let's have a look at that example of that in action. In this case, in fact, let's look at the code on GitHub. That's probably the best place. So if we look at the JavaScript for this, try and bump this up, you'll see that we have 3 different constraints. That's pretty big. We have 3 different constraint values, each specifying a different size for the image. When we press the button, depending on which button we press, we get a different constraint. And you can see, you can actually read that. That's the actual video size you're seeing there, got from, you know, video height, video width. And we can get, in this example, QVGA, VGA, chug, or even more pixels like that. So yeah, we can specify what we want from the camera in that case. Like it said on the previous slides, scaling and cropping hasn't been implemented, so it is from a fixed set of values. Another example, a little bit more complex here, is the ability to use constraints to select the camera. Again, I'll just show you briefly the code for this on GitHub. If we look at the JavaScript, you can see that when we open this page, if you can see there, we're using the MediaStream track method getSources. This is getting a list of devices that are connected to this machine that we could use as a source of for media. And in the callback for that, we're setting those values in a select, so we can select the microphone and the video camera. And when we go to call getUserMedia, we're given constraints which are based on the current value of the select, so the ID of the microphone or the ID of the camera. So if we look at this now, you'll see that I only have one video source available there. If I plug in this handy camera and refresh the page, let's have a look. Let's see. Hang on. You can see I've now got a choice of two cameras. And I can go back to the other one. Okay, hang on. Let me go back to the camera. Now, this really comes in handy for mobiles. So I will attempt to use this camera as a cheap and cheerful sort of wolf vision device and show you this working on my phone. So I'm using Chrome Beta here. By the way, if you want to download Chrome Beta, you can't get it directly from the Play Store. You need to go to a browser on your phone, Chrome is good, and find it from there, and then you can install it from a link. So I'll just try and do this so you can see it. This is hard. So, okay, I'm getting user media here, and you can see it's choosing the the front-facing camera. In this case, it's called camera 1. And then if I move over to the rear-facing camera, then you can see that I've sort of got a video of you lot. Anyway, there we go. But obviously that, the real power there is for mobile devices. A couple of things that are coming up. You will have the ability to choose source with, I'll actually show you the spec, with the facing mode enum, which is this catchily named thing, which kind of does the same thing, but enables you not to have to specify an ID for a device, but generically say, I want the user-facing device or the environment-facing device, or left or right, and so on. We're also going to get the ability to use the apply constraints method, which means you can dynamically change constraints from JavaScript, which again will be very powerful for doing stuff on the fly. I think, again, coming back to this idea that the real power of WebRTC is when it comes up against other APIs. We have the ability to integrate web audio with getUserMedia. And what this means is you can use the output from your microphone, or the input from your microphone, as the input to web audio. So using the create MediaStream source method here, which you can see is getting a stream from the getUserMedia callback. Let's have a look at that in practice. A demo here by my colleague Chris Wilson. So there's the call to getUserMedia, asking for permission. The stuff from the audio from the mic is being fed into web audio, which is then analyzing that audio and doing this nice canvas visualization. And then we can also use recorder.js to record that stuff. So blah, 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 and then download it. There we go. Now I've lost my presentation. Okay. So again, just loads of potential there for working WebRTC into other APIs. With constraints, we also have the ability to get video from other sources. The obvious example of this is screen capture. So we have the ability to set the source to be whatever you're seeing on screen. So a little demo of that. If I come out of full screen, you can see I have to accept, give permission to do that. And then if I just move that around a bit, you'll see we've got screen capture happening. Kind of slightly useless, but yeah. The other way of doing this is actually the tab capture interface for Chrome apps, Chrome tab capture, which allows you to get a single tab, which is a whole more potential, I think, the ability just to define one single tab. We've just seen implemented in Firefox, which is fantastic, the MediaStream recording API. And we have an intent to implement that in Chrome. Just to show you a little example of that running in Firefox nightly. So what we have here is getUserMedia being called, and in the callback for that, a media recorder object is instantiated, and then that's essentially creating a blob of recorded data. I don't know if anyone heard that, but which in this example is just being played out in an audio element, but you could download that as well. So this, the aim of this, of course, is to enable recording of audio and video streams. If you're interested in this stuff, you might want to look at the Streams API, which is a kind of generic concept for streaming data, which is in the process of being specified. A lot of people have asked for specifically the ability to essentially take photographs. And again, of course, this is crucial to apps running on mobile devices. Well, we have a spec for this. It essentially has two methods. One is getFrame, which gets a frame full of image data. And the other method is takePhoto, which kind of does what it says and creates a blob's worth of image that you can access from an onPhoto handler. So yeah, that's coming up at the moment and worth looking at the spec. So this stuff is great, but of course it only becomes really powerful when we can use this for streaming between peers. So in order to use communication, we need this API, and the API is RTCPeerConnection. So RTCPeerConnection enables connection between two peers and then does the work of streaming audio and video data. So the concept, in a sense, is quite simple. You've got a media stream on one side, pump that into RTCPeerConnection, and then you get a media stream out the other end. Of course, RTCPeerConnection has to do a lot. There's a lot that goes into this. RTCPeerConnection has to do things like noise reduction, sort of like little things like, which are hard work, like echo cancellation, what's called dynamic jitter buffering, which kind of stops video hiccups, and the whole process of enabling smooth communication even when there are bandwidth hiccups and so on. This diagram is kind of really there just to show you that a lot of stuff goes on that you don't have to worry about as a web developer, thankfully. WebRTC does a lot behind the scenes. Now, kind of guilty secret about WebRTC is that despite being peer-to-peer, we still need servers to build WebRTC apps. It's not possible at this point in time to be able to kind of, I don't know, for an app to sort of shout out into the internet, connect me to my friend, stream data with my friend. Yeah, that would be great. It just doesn't work like that. So we need servers for two things, essentially. We need to be able to exchange metadata between peers in a WebRTC conversation. That's called signaling. And we also need servers to cope with the real world of NATs and firewalls. And these are called stun and turn servers. And the whole framework that uses them is called ICE. And I'll go into some more detail about this. The architecture around this, which has been specified in the ITF, is called JSEP. The kind of simple idea here is just that your signaling goes via some unspecified mechanism, and that then that can enable media streaming directly between the caller and the callee. So there are these two processes going on. It's a simple point, but it's kind of at the core of the architecture of WebRTC. So for signaling, we need to be able to exchange these things called session description objects. Firstly, we need to, for WebRTC endpoints, to swap information about media. So this is like the codecs that I support and the codecs that I'm going to be sending, information like that. Now, the other part of this is for peers to be able to swap network information. So this is the kind of IP and port that a device can be accessed from. So in other words, when you want to make a connection, you need to contact the peer that you want to communicate with and give them network information so that they can actually then set up a conversation with you. WebRTC deliberately doesn't define any messaging mechanism. You can use what you like for signaling, and there is no messaging protocol defined either. And the thinking behind this is that these things are changed, different people have different opinions, so that shouldn't be mandated in the WebRTC specs. Of course, signaling can also be used to exchange application data. So when users are beginning to with the process of initializing your app, then they can exchange data using the same signaling setup. So how are we going to do this? Well, the kind of core part of this, of course, is that signaling needs to be bidirectional. So if you imagine like Fred wants to call Wilma, well, Fred's going to have to go via a signaling server, and Fred is going to have to be exchanging messages with the signaling server to start with, and then when Wilma gets involved, there's going to be signaling messages going from Fred via the signaling server to Wilma, and then from Wilma via the signaling service back to Fred again. Now, of course, with HTTP, the kind of request-response model, this in the past maybe has been a bit tricky. You could do this by repeated polling, like Fred's WebRTC app could keep asking the signaling service, have you got a message from Wilma? Have you got a message from Wilma? This would be inefficient, and of course, it's not going to scale. Although, a matter of fact, I've seen apps where actually, this, with a bit of optimization, this can actually work. Another alternative is to do long polling, Comet, whatever you call it, to enable sort of fake bidirectional communication with a server. This is actually used by the Google App Engine, the channel API, with some of the examples I'll show. You could actually use Ajax, XHR, and event source. Event source is the API for enabling what are called server-sent events. So for a server to maintain a connection with a web app and send, push data from the server to the web app. There's a demo there if you want to have a look at that in action. Possibly a more natural solution is WebSocket, which is, of course, inherently bidirectional. And this is supported by all the browsers that support WebRTC, desktop and mobile. And of course, you can use TLS with WebSocket, which is secure and avoids some proxy problems and so on. If you want to read more about that, I'd recommend looking at Ilya Gregorik's chapter about WebRTC, which is just coming out, and Peter Lubber's stuff there is great as well. I've actually built a code lab for this if you want to have a go at building a signaling server. This uses Socket.io running on Node. Of course, the only catch with this is that you need to have a server running Node, and the obvious retort to that is that a lot of cheap hosting services only support, PHP or whatever. So for those situations, you could use event source, XHR or whatever. But if you want to have a look at this, I'd recommend this because it's very simple with Socket.io use Socket.io to exchange messages. If we look at the Code Lab code, in fact, you'll see that, and this is just the signaling part, there's no WebRTC in this, but you can see that, you know, that's the code for the server, which is pretty straightforward. And if we look at the client code, likewise, for this app, it's really, really simple to build, you know, build a signaling service running on Node with Socket.io. And there's a live example there too, if you want to have a look at that running on Node just too. A couple of gotchas there, go into the detail, but just one thing to remember, if you do build a signaling service, you know, inherently signaling is not high bandwidth. These are tiny messages, mostly exchanged at the start of a WebRTC call. But, you know, of course, if you have a lot of users, then the load can still be very heavy on a signaling server. So, when RTCPeerConnection objects are initialized, they have to do a couple of things. They first have to ascertain the local media conditions. So this is the stuff I was talking about with resolution, codec capabilities, and so on. And the second thing they need to do is get you know, these network addresses that potentially the callee can use to contact them on. These are these things called candidates. So the media process, the process for exchanging media metadata, works a bit like this. So again, it's like, imagine Fred is calling Wilma. Fred calls the RTCPeerConnection create offer method. And this gives a chunk of SDP, session description protocol data, which tells stuff about local media conditions. Fred then sets that as the local description. At this point, by the way, you can tweak stuff with codecs and so on, so that's why that process can be done manually. And after Fred has set that as his local description, he can then serialize that data, send it to Wilma. Wilma kind of does the same thing in reverse, but that's called the answer. So you have this offer-answer process. Fred creating media metadata, setting it locally, sending it to Wilma, Wilma creating her local media metadata, setting that locally, sending it back to Fred. And then they both have what's called a remote description. There's a kind of similar process which happens around the same time of finding network information. So the way this works is that Fred and Wilma create their RTCPeerConnection objects. If that's successful, the ICE candidate events start propagating. And in an ICE candidate event, you can get these things called candidates, which are information about how that peer can be contacted. In other words, an external IP and port by which the host device for that app can be contacted. So Fred and Wilma both get these candidates and then they start firing them at each other. And when they receive them, they use add ICE candidate to give that information to RTCPeerConnection. So this way, they're exchanging network information in order to be able to set up the call. This is what an RTC session description looks like. So this is media metadata. This is the offer-answer part of it. This is the kind of stuff that's being sent over. If you want to know what all these things mean, and the actual data is a lot longer, a bit longer than this, check out the ITF examples with detailed explanations. And this is an example of a candidate offer. A candidate object. So the candidate here, the data, the bit that you see, the candidate values there. I did this on localhost, but this was got from in the ICE candidate event, and you send a bunch of these candidate objects to the person you're trying to communicate with, so they can try and make a connection with you. If you want to see this whole thing in action, I won't show you now, but it's a really great example on the W3C site. It has the whole process of peer connection with signaling. Just to show you a kind of demo of SDP. Sorry, this is a bit hot off the press, slightly rough. So in this example, we're getting a local media, and then I'll create a peer connection object, and then I'll create an offer, and then you can see that's an entire chunk of SDP for an offer. And I could actually edit that if I wanted to kind of tweak codec values and so on. So I'll then set that offer as the local offer, and it'll be passed to the other. This is kind of silly because it's two peer connection objects in one page, but you know, you get the idea. And then I can create the answer, which is kind of similar, but from the other side, set that answer, and then we have a peer connection. Something that's just been implemented, which to me I think is really powerful, is this idea of being able to use the output from one RTC peer connection, like MediaStream from one RTC peer connection, as the input for another. Now, the reason this is interesting is that it gives us the ability for a web app to choose how to forward a stream to another peer. So in this, again, it's all on one page, so it's slightly pointless, but I'll start by getting some media, and then it's displaying it in a video element. I'll call to this second peer connection object, and then it's going through a whole bunch of other peer connection objects to this final peer connection object, and then playing that media stream out in another video element. So it allows web apps to choose how they forward streams to another peer. If you want to look at peer connection, get your head around this, this is a good place to start. This is peer connection without any signaling. It's about 100 lines of code, shows the whole process in action. If you want a kind of full-fat video chat app, this is the kind of canonical Google chat app with lots of logging to the console, very good for if you're trying to work out the kind of processes, the sequence of events. Like I said, we also have the ability with WebRTC to communicate arbitrary data. And you know, I think this is, I think for a lot of people actually, this is one of the most powerful parts of the project. There's some kind of obvious use cases. So you imagine two people playing a game, and they need to communicate arbitrary data like this, which is actually completely faked, but you get the general idea. So you might be communicating player positions with another player, and need to do that with as low latency as possible. The API for DataChannel, RTC DataChannel, is very similar deliberately to WebSocket. But of course, the point about DataChannel is that they go, you know, you're exchanging arbitrary data directly between peers. You're not having to go via an intermediary WebSocket server. You can optionally choose that communication, the transport, to be reliable or unreliable. What that means is that if you say the communication has to be reliable, then what you're saying is this must fail unless every packet is delivered. And obviously you're going to need that for stuff like, I don't know, file sharing, whatever. If you say that you're happy with better performance, but it can be unreliable, then that kind of, I don't know, that's okay for things like, yeah, exchanging game player positions, stuff that where you don't actually have to get every piece of data. Reliable transport has been implemented SCTP in Firefox for some time, and now in Chrome 31 and Chrome 30 behind a flag, which is great. Yeah, the API looks like this, which, as you can see, is pretty straightforward kind of addition to peer connection to specify that you want to use a data channel, and then when you get the data channel, you can set up the channel to handle messaging, very like with WebSocket. Again, a really simple sort of one-page example of doing that if you want to have a look at how data channel works. A slightly more exciting demo, I think, is the ShareFest app. This enables you to share files using RTC DataChannel. So I'll choose, this is a photo of my local pub in Tooting in London, which we're trying to save from being developed. So I've specified that as the file that I want to share via RTC DataChannel, and then I just need to pass someone the URL for it, which is here. So you have to pretend this is on another machine, but you get the general idea. So yeah, I've just kind of communicated with myself this photograph, but you can imagine that that being very powerful. The ability to to share files without some kind of intermediary file service. So, like I said, you know, in a perfect world, it would all be like this. We would just do this communication directly between peers. Of course, in the real world, we have NATs and firewalls. We need to be able to cope with that in order to establish streaming between peers. So we have this well-established, actually, technology for this called Stun. A Stun server has a really simple task, which is just to, when a request is made, to respond with a public IP and port that the requesting device can be contacted from. So it's you know, it's a simple server. It doesn't do much. It's kind of relatively cheap to run. And yeah, that's kind of the way it works. The Stun server living on the public internet outside the firewall. If that fails, we have another method, which is to use a turn server. A turn server is essentially a relay server. Again, this is living on the public internet, and the idea of this is that if, because of complex firewalls, NATs, and so on, direct peer-to-peer communication fails, we can go via this relay server called a turn server. Now, the downside of that, of course, is that essentially those turn servers are relaying all the streaming data. So they don't have to be particularly smart, but they are dealing with a lot of bandwidth. So that's the cost there. This, if you look at the RTC app I mentioned, this is the value that's passed into the RTCPeerConnection object to specify the stun and turn servers with some login details there. It's optional to use stun and turn, but that's the kind of thing you'll be doing if you want to use those servers. The framework that is used by RTCPeerConnection to work with these technologies is called ICE. So, you know, if the trade-off here is that stun, of course, is cheap because all you're doing is getting an external IP port for a device. Turn is kind of works in every case, but it's more expensive and it's less efficient. ICE works with a whole list of candidates, which I showed earlier being passed between peers. ICE works with that list of candidates to find the optimal path. And in fact, the majority of calls between peers will actually work directly peer-to-peer with the help of stun. It's around by these stats around the sort of kind of 6 out of 7 work out okay that way. It is slightly less between business-to-business calls. If you want to run a stun server, there's some options. Google has a test one, which you can use for testing, and there are open source implementations, the RFC 5766 turn server, and there is a VM image available for that for Amazon Web Services. Just a quick word about security. A lot of people ask about this. It's kind of core to the WebRTC project. We have mandatory encryption with all the components of WebRTC, and of course, like I showed you, we have UI interactions designed to be secure. You have to explicitly opt into participating in a WebRTC call. I think that, though, that the most secure aspect of this is, of course, that WebRTC is built into the browser. So it's sandboxed. There's no plugins. There's no separate update process. There's no way to kind of trick people into installing extras. So we have, these secure pathways. This should actually say TLS rather than HTTPS because you might be working with WebSockets, but everything is secure in those encrypted in those processes. Just to reiterate, though, when you're building signaling, you must use TLS. Otherwise, if your signaling is prone to being intercepted unencrypted, then of course that opens up lots of potential for kind of man-in-the-middle stuff of redirecting calls and so on, and intercepting stuff, maybe injecting stuff and so on. So it's really crucial with signaling when you implement that to use secure protocols. So we have in the simple case, connection with WebRTC between two different devices. We could actually, and this works for lots of WebRTC apps, the ability just to create more RTCPeerConnection objects and to use those to connect lots of devices to each other in different kind of configurations. Now, this doesn't scale, of course, and the kind of robust answer to this is to use something called a multi-point control unit. These are servers specifically designed to handle media to enable some clever stuff too, like coping with media coming in with different codecs and resolutions and so on, and to be able to do kind of efficient distribution of that media between lots and lots of peers. So WebRTC has been designed for these kind of different topologies, but also to enable communication with the outside world. So in particular, thinking of phone systems, there's a stack of stuff that's been implemented to enable WebRTC to work with SIP clients. This is like voice over IP and video conferencing systems. And also some phone APIs from Phono, which is kind of integrated with jQuery, and the Zingaya embeddable phone widget. Check that out to connect to PSTN. PSTN is like the plain old phone network. Really nice thing. Sorry, I keep bringing it every time I talk. I show this. These guys from Voxio and Tropo, they did this, I think, at Burning Man this year. They set this up for us at Google I/O a couple of years ago. They built their own mobile network using the open BTS, open source cell network. And what that meant was when they incorporated that with their gateway to WebRTC, that you could make phone calls from any old phone through their gateway, through their open BTS cell, to a WebRTC app running on a computer, which to me is fantastic. This is telephony without a carrier, and this is really, really useful in situations where there is no infrastructure or infrastructure has been damaged. So a lot of potential for that stuff. Just a quick pointer to some tools to help you building WebRTC apps. Chrom has a WebRTC internals page which gives stacks and stacks of stats and so on about what's happening with your WebRTC connections, and you can download the whole lot and see. It's actually nice when you're trying to get your head around WebRTC to be able to look at all the signaling data from there. Another, what's a JavaScript shim maintained by Google, Adapter.js, kind of abstracts away some of the differences in prefixes and so on. The spec is pretty stable now, but has enabled you to use the same terms without having to change that each time there's a change. If all this is too much, then I recommend these JavaScript frameworks. There are a stack of good, mature JavaScript frameworks for building WebRTC apps without having to go into the whole process of stuff I was talking about. I haven't got them here actually, but there are also these Simple WebRTC has a signaling server too called Signal Master. So Simple WebRTC is very straightforward. It's really easy to build an app with a few lines of code. Likewise, Peer.js does the same for DataChannel, just kind of 10 lines of JavaScript. If you don't want to write any code at all, there are lots of complete services now on the web, OpenTalk, VLine, and others, Asterisk and so on, enabling WebRTC calls without doing any work to implement anything at all. And of course, the old C++ code is there as well. If you want to have a look at the package, you can check out that. If you want more information about WebRTC, I maintain a list, which is at the top there, which is kind of all the stuff I know about and have heard about, and get some contributions to that as well. And yeah, I'd recommend taking a look at the Google I/O presentation that Justin Aberti and I did this year. A lot of good stuff there. Lots of ways to contact WebRTC people. The main forum for technical discussion is Discuss WebRTC, the Google group, and a stack of New stuff is always being posted on Google plus WebRTC. And we really welcome, of course, people's feature requests and bug reports. So keep them coming on crbug.com/new. And yeah, what interests me is what web developers do with WebRTC, kind of out of the worlds, beyond the worlds of kind of telephony and video conferencing and all that. So I'm really interested to see what people like, you in this room will be doing with these APIs. I just wanted to finish by actually doing some WebRTC chat. If anyone's got a browser, if they want to go to this page, it's talkie.io/GoWebRTC. I'll just see if we could have a video chat between whoever shows up. I don't know if this is going to work. If anyone's got a... I'll just show the URL again. So if anyone wants to join this, we'll see if we can get people up on this. Is it going to work? Maybe not. We're on two different networks here. Oh, here we go. Hello, whoever you are. Sorry. I think that's it. We got someone else? This is cool. And this is kind of brute force method, just lots of RTC peer connections. That's brilliant. I recognize that bloke. Okay, anyway, I better finish up. Like I say, the slides are online at gowebrtc.appspot.com. And yeah, thank you so much. I've got a couple of minutes. I don't know. I'll take some questions. Thank you. Thank you. I don't know if I'm going to be handed a phone with questions or... Oh, yeah. Okay, I'll try to answer these. What about Firefox and IE? Well, we've got support for Firefox, which is great. IE, of course, has had full support with WebRTC via Chrome Frame, but sadly not in the future. IE, we don't know. Some people may have seen the CU WebRTC proposal, which is, I think, it's a lot of comments on the existing WebRTC proposal. So I think it's very compelling when we have WebRTC on, once we start having WebRTC endpoints of like billions of them, it becomes very compelling for IE and Safari and so on. So we'll see where that goes. Does it make sense to include location awareness into WebRTC? That's really interesting. Yes, definitely. I can think of lots of use cases for that. That's a really good point. People being able to contact people who are, looking maybe to answer questions and so on within the vicinity. The next question is, what codec is used for sending the data over the wire? Is it possible to control the bandwidth or auto-tune according to available resources? Yeah, kind of. You can tweak the STP that you set as the local description and send to the callee that they then use as the remote description. So you can tweak that stuff. And the codecs you use are, what are implemented by the app. So for Chrome, we've got, VP8 and Opus, but you can tweak the details for that. Yeah, if you need more information about that, go on to the Discuss WebRTC group if you need more specific stuff about that. Can RTC handle CGN, Carriergrade NAT, where individual clients are behind multiple layers of NAT? Yeah, that's a good question too. My little diagrams show kind of one little NAT, and it's all very simple, but in the real world, it's more complex than that. You may have firewalls and NATs behind NATs, and so on and so on. It depends. I'm not very expert about this, but it kind of depends on the stun server. But obviously this can be a problem, and this is where we have turn servers to provide a fallback, sadly, for that complexity, which we, of course, get particularly with businesses running with these very complex and potentially, like sometimes outdated network setups. But yeah, it's complex, and I don't really have a good answer for how we can, develop stun in order to cope with these, I guess, increasingly complex NAT setups. Now this is great. Any thoughts on P2P CDN via WebRTC? I meant to show this off. Possible users worried about bandwidth. I think this is a really interesting area. So the idea is that you don't just do file sharing like the stuff I showed with ShareFest, but you do something like what, I don't know if anyone's seen PeerCDN. The guys are called Peer5. Have implemented this stuff, and it's a really interesting concept. It's kind of peer-to-peer file sharing. So conceptually, the idea is that you would be able to get assets not by default from a server, but by default from some other peer that hopefully, of course, is close to you network-wise. Now, in a sense, this is exactly the kind of thing that we could see with RTCDataChannel, this ability to work with files or chunks of files. It could be the kind of P2P dream come true. Of course, the great unknown is how that will work in practice, and I don't have an answer to that. How efficient that can be, whether that can work well, how that works with bandwidth. Like any peer-to-peer system, if I'm suddenly working as a redistributor of content, we don't know how that would work if everyone started using PeerCDN and started distributing content peer-to-peer via WebRTC. So I don't know the answer to that, but it's I think a very interesting area for peer-to-peer file sharing and file distribution, really. CDNs running peer-to-peer rather than from these kind of monolithic server setups. I think that's the last question. If anyone has more questions, I'll be around today and tomorrow, so please feel free to come and talk to me or email me. My email is dutton@google.com. So thank you very much.